Chi-square hypothesis testing, chapter 14. I'm going to introduce the chi-square distribution. A population can be divided according to gender, age group, type of personality, marital status, religion, annual income, political affiliation, education, and more. These divisions are known as classifications of the population. And notice that there are no numbers involved with classifications. So either, if you can consider a classification of gender, we're not going to judge, or we're not going to categorize somebody's gender based on a number. We're going to categorize somebody's gender by categories, male and female. Age group can be described using numbers, but they're groups of numbers. So we would maybe categorize somebody in an age group 1 to 18, another age group 18 to 25, another age group 26 to 34, and so forth. Type of personality, again, are categories. Marital status, single, married, divorced, widowed, those are categories. Religion, etc. So if we remember the earlier part of the semester, we did talk about categorical data. And the chi-square distribution is basically built on categorical data. In this chapter, we will explore a technique that determines if two classifications of a population are independent, which means they're unrelated, or dependent, meaning that they are related. And here are some questions that we can ask. Are annual income and education dependent or independent? So are they related or unrelated? If they are dependent or related, we would expect people with low levels of education to have low incomes, and people with high levels of education to have high incomes. If they are independent, we would expect people with high levels of education to have low incomes, and people with low levels of education to have high incomes. So independent means unrelated. Are movie preference and gender dependent or independent? So are they related or unrelated? If they are related, dependent, then the relationship between classifications might be that females generally prefer romance-type movies and males generally prefer adventure-type movies. So you would see more females choosing romance and more males choosing adventure if they were dependent. If they are independent, then knowing one's gender would not give you a clue as to their movie preference. Are male personality types and incidence of heart attack dependent or independent? If they are dependent, we would expect to find males with type A personalities more susceptible to heart attacks than other types. If they are independent, then one's personality has no relation to the incidence of heart attack. So in each of these examples, we have categories, two categories specifically. Male personality types would be the first category. Incidence of heart attack would be the second category. And we want to know if we have dependence or independence. So we want to know if the two categories are related or unrelated. The chi-square test of independence is a statistical technique used to investigate whether the classifications of a population are related. A random sample is selected from a population. The sample data is separated into different categories for each classification of the population. This is an example of the data after it's been categorized. So along the top we have the classification for movie preference, and along the side we have the classification of gender. And for movie preference we have the different types of movies, and for gender we have the two different genders. The number of responses falling into the categories for each classification are recorded into a table. These are called observed frequencies. The table is referred to as a contingency table. A contingency table has a row classification and a column classification. The column classification is movie preference, and we have 5 categories: romance, comedy, drama, adventure, mystery. So these first 5 columns are the most important for our purposes because they contain the real data. And then we have this row total, which basically comes if we get that number if we just simply add up the numbers in a particular row. The row classification is gender, which is separated into 2 categories, male and female. So we have 2 rows containing data, and the last row of the table is just simply a row for totals. So if we were to just take 10 and 50 and add them up, we get the number 60. 60 is not considered data from the table, it's considered just a total. Each individual table entry is called a cell. The cells are labeled A through J. So if you take a look in the upper left corner of each cell, you have the letter A, B, C, D, E, F, G, H, I, J. So those 10 cells are the cells that contain the data. And each of those numbers are called observed frequencies. It means that of our sample, and the sample size can be easily seen if you go to the bottom right corner of the table. Where the row total and the column total meet, we have the total sample size, and it's 200. Of those 200 people, 10 males preferred romance movies above all else. 20 males preferred comedy movies above all else, and 5 males preferred drama movies above all else, and that's how we read the table. So they're called observed frequencies because they are what we observed in our sample. Okay, so some observed frequencies that we notice: the number of males who prefer adventure movies over all other types of movies is 40. So we go to the row male, we go to the column adventure, and that number is 40. The number of females who prefer romance movies over all other types of movies is 50. There are a total of 90 males, so you go to the row labeled male and you go to the very end, the row total is 90. There are 45 people, meaning males and females, who prefer comedy movies over all other types of movies. So we go to the comedy column, we add up the males and the females, so 45 people total who prefer comedy movies. So again, they are called observed frequencies because they are what we have observed in our sample. Expected frequencies are slightly different. Consider that there are a total of 90 men and 110 women. If there are 60 people who like romance movies best, and gender and movie preference are independent, meaning that they're unrelated, how many males and how many females would you expect to like romance movies? So if they were unrelated, independent, and you had 60 people who liked romance movies, if you examine those 60 people, how many would be men and how many would be women? Well, it wouldn't be exactly 30-30 because there are less men than women in the sample. There are 90 men in the sample and there are 110 women in the sample, so it wouldn't be 30-30. There'd be less men, so maybe a little bit less than 30 men and a little bit more than 30 women. But we could figure this out exactly if we had to. If we take the ratio of men to the total number of people in the sample, we have 90 to 200. If we consider the fact that we have 60 people who like romance movies best, we can figure out how many men we would expect to like romance movies using this proportion. Number of men to total equals X to 60. So the proportion of men to total is equal to X over 60. If we do the cross multiplication here, we can solve for X, which gives us the total number of men in the group of 60 who we would expect to like romance movies. Now, it's going to be a little bit less than 30 because it's not 30-30. As I said, we have less men than women, so it's not going to be 30-30, but it is going to be close. So if we cross multiply, we have 90 times 60, and then we have 200 times x, and we'll solve for the equation, solve it for x, and you get 27. So if you need to understand how to do that, 90 times 60 is 540, and then you say equals 200x, and then you divide both sides by 200. So if you go to your calculator, 540 divided by 200, no, I'm sorry, I'm off again. It's not 540, it's 5400. 90 times 60 is 5400. So we take 5400 and divide it by 200, that gives us 27. So if we have an unrelated classification of romance movies, and we say that romance movies in gender are independent, then we would expect 27 people out of that sample 60 to be men, and the remaining 33, because 60 minus 27 is 33, the remaining 33 would be women. Now, in reality, you should probably get the feeling that this is unlikely. It's more likely in our society, knowing what we know about movie preference, it's highly probable that most of the women of this sample, or most of the people of this sample, are women and not men. So it probably will not be as high as 27. Okay, but if there were no relation, which means independence, we would expect 27 men and 33 women to like romance movies. So our expected values are values that we would expect to get if there were no relation between the two classifications. The values in the contingency table are observed values taken from a particular sample. So we have these observed values that we've actually observed from our sample, and then we have these expected values, what we would expect had there not been any relationship. To test whether the two classifications, gender and movie preference, are related, we compare the observed frequencies from the table to expected frequencies. The expected frequencies will be determined assuming that there is no dependence between the two classifications. So using that proportion method, you can find out what the expected frequencies are for each of the categories. So for males and romance movies, and then for women in romance movies, for males and drama movies, and women in drama movies, etc. So each cell has an observed frequency that's in the table and an expected frequency that can be calculated from the table. The comparison of the observed frequencies and the expected frequencies, assuming that there's independence, is calculated using the formula here. O stands for observed frequency, E stands for expected frequency. If all the observed frequencies in every cell if we subtract O minus E, square it, divide by E for all the cells of the table, and then add up all those results, we have a value called chi-square. Chi-square is called Pearson's chi-squared test statistic. It is another form of a test statistic like x bar and like p hat, in that it describes some characteristic of the sample. O represents observed frequencies from the cells of the table, and E is the expected frequency of a cell in the table. So for all the cells in for all the cells in the table, you're going to take O minus E, square it, divide by E, get answers, and then sum them all up. It can be done using a chart similar to the way we found the standard deviation by hand, but we're going to be calculating chi-square on the calculator. If you want to see how this is done by hand, the textbook, chapter 14, will show you step by step exactly how you can go from a contingency table to calculating the chi-square test statistic. And basically, the chi-square test statistic is a measure of how related two classifications are. If chi-square is small, meaning it's close to 0, then we can conclude that the two classifications are independent, so not related. If chi-square is small, then we conclude that things are not related. When the observed and expected frequencies are exactly the same, chi-square equals 0. So if what you observe and what you expect are exactly identical, chi-square is equal to 0, and that's perfect independence. Any positive value of chi-square indicates that there is a difference between the observed and expected frequencies. The larger chi-square, the larger the difference between the observed and expected frequencies. So, the larger the difference between what's observed and what's expected if there is independence, indicates that we have a larger chi-square. So chi-square will never be less than 0. It will never be negative because the calculation of chi-square involves squaring, which never results in a negative value. So we want to keep a couple things in mind here. Chi-square starts off at 0 and only gets larger. So possible values that you can get when you do the chi-square calculation is anything from 0 and greater. And the other thing to keep in mind is that independence occurs when chi-square is small or close to 0, and dependence occurs when chi-square is large or farther away from 0. The larger chi-square, the larger the difference between the observed and expected frequencies, and the larger that difference, the greater dependence you have. So a large chi-square tends to indicate that there is a significant relationship between the two classifications. So how large does chi-square have to be to definitively say that the two classifications are dependent? So to answer the question, we have to conduct a hypothesis test. Like in our previous examples, testing a mean, testing a proportion, testing two sample means, we have to know exactly how far away from center does our test statistic have to get in order for us to reject the null hypothesis. And that's the same concept that we have here. We use a distribution of all possible values for the chi-square test statistic. It's called the sampling distribution of Pearson's chi-square statistic. And this is the appearance of the distribution. It's not bell-shaped. It is a skewed distribution, and it's skewed to the right. You can see that it begins at 0, and along the horizontal axis are placed basically values for chi-square. So the value of a particular chi-square can be positioned anywhere along the horizontal axis. The collection of all possible chi-square test statistics form this skewed right distribution called the chi-square distribution. It's never negative, it's always 0 or greater. And those values in this location on the graph indicate that we have smaller values of chi-square, and over here we have larger values of chi-square. Over here we have the meaning of the chi-square that we get would indicate that the two classifications are independent or not related. If we get a chi-square far over here, it would indicate that the two classifications are dependent or related. Okay, the graph of the chi-square distribution is not symmetric. It's skewed right and extends infinitely to the right of 0. So notice that the top of the curve comes lower and lower, but it never quite touches the horizontal axis. That indicates that it does continue to the right forever. Now the amount of area underneath the chi-square distribution is 100%. There's a family of chi-square distributions in the sense that they tend to look different with differing degrees of freedom. The look is dependent on the number of degrees of freedom. The degrees of freedom are found with the calculation rho minus 1, R stands for rho minus 1 times column minus 1. And the rows come from the contingency table and the columns come from the contingency table. R is the number of row classifications. So remember that in the contingency table for movie preference versus gender, there were two genders, male and female, but there were actually 3 rows on the table. In that case, R would be considered 2 because there's only 2 classifications for gender, male and female. C would be the number of column classifications, and there were, I believe, 5 of the gender, 5 of the movie preferences. I'll go back and double check. 1, 2, 3. Yes, there were 5 movie preferences, and so 5 movie preferences indicate that C, the number of column classifications, is 5. So if we were to look at the degrees of freedom for that contingency table, we would take 2 minus 1 times 5 minus 1, which is 1 times 4, or 4 degrees of freedom. And you could take a look at the graph here, what 4 degrees of freedom looks like. It kind of takes on a different shape than some of the others. Now, we don't really have to worry too much about the shape of the distribution based on different problems because every problem is going to be conducted in the same way. We're going to just assume that we're looking at a skewed right distribution every time we do chi-square, but keep in mind that it does change shape if you were to compare one contingency table to another contingency table. As df increases, the chi-square distribution approaches the shape of the normal distribution. So df is, remember, our degrees of freedom. Look at what happens when it approaches 20. It almost looks like a bell-shaped curve, and that's going to happen as your degrees of freedom get larger. So it's going to almost look like a normal distribution when df is large. We will not see a df that gets any larger than 20.